process is process C to D. So you can see from process C to D, this is actually isothermal compression process, as the volume is being decreased and slightly increase in pressure. And in this process you can see Q is been rejected, that is why Q out, I have denoted it Q out over here. Okay, now so as heat is rejected, so I have to calculate the amount of heat is being rejected, that it heat rejected at CD process, which will be equal to the work done in this CD process, because the amount of heat is being rejected is the work done of that CD process. So WCD is equal to PCVC, that is the initial pressure and volume of this point C or the state C, and the log of E, and this change in volume from C to the Vc by Vd. Okay, so now this PCVC can be replaced by this RT2. Why? Because again we know this is PCVC will be equal to RTC, and this TC is equal to TD is equal to T2, as it denotes this line. This is isothermal line. TC is equal to TD is equal to T2, that is the lower temperature. So by this way you can find out the work done, that is RT2 log of E Vc by Vd, and that thing can be represented by R2. R2 is nothing but isothermal compression ratio. As the volume is been decreased, that is why we are taking Vc by Vd, that is the compression ratio. So students, let's move to the next process, that is process D2A. So you can see process D2A, the slight decrease in volume but rapid increase in pressure, which denotes the compression process, and that too the adiabatic compression process. That is why I denote by the red ink. Okay, so you can see as for B and C, B to C, we actually use the adiabatic expansion process, and then the relation between the temperature and this expansion ratio. Here also we will be using another relation of temperature and compression ratio, that will be higher temperature by lower temperature is equal to R to the power gamma minus 1. Gamma is the adiabatic index, whose value is 1.4 for air. Now the R is actually the compression, adiabatic compression ratio, adiabatic compression ratio. Okay, now you can see the higher temperature, because at state A it will attain the higher temperature, so TA is the higher temperature and TD is the lower temperature. So in this process D2A, TA is the higher temperature, TD is the lower temperature, is equal to Vd by Va, as it is a compression process. So that is why Vd is the most excess volume than the Va. So that is why Vd by Va to the power gamma minus 1. Now as we know, this Ta is equal to Tb is equal to T1, as it is an isothermal process, and this Td is equal to Tc is equal to T2, that is also isothermal process, and this T1 is the higher temperature and T2 is the lower temperature. So we can replace Ta by T1 and Td by T2 is equal to Vd by Va to the power gamma minus 1. So this thing we will be using in our efficiency formula. Now one interesting question arises for the each case of this isothermal compression as well as isothermal expansion. That means isothermal expansion means when A to B, process A to B, and this compression means process C to D. For both the cases, or I can say for isothermal heat addition or heat rejection. So in these cases, why I actually consider the heat added as the work done or the heat rejected at the work done. So actually when I use the term heat added, then I should use this Q1, it will denote the heat addition. So from the first law of thermodynamics we know heat added or rejected is equal to work done plus change in internal energy. That is why the change in internal energy is neglected over here, as the process is isothermal process. So that is why the heat added, that is Q1, is equal to the work done, okay, over process A to B, or the heat rejected, that is Q2, is equal to work done at process C to D. So that is why we are actually directly converting the heat addition to the work done and heat rejection to the work done.